this video, I'm going to show you how a simple table, barely more complicated than a tic-tac-toe grid, can help you solve overlapping sets problems. This problem, which I've written in the style of a GMAT problem, concerns the students at College X and focuses on whether they own a bicycle and whether they own a car. A common approach to this kind of problem is to make a Venn diagram. In this case, that would involve making one circle for the bike owners, another for the car owners, and then a big rectangle for the whole universe of the problem, the students at College X. Now, I've already promised you that the best way to solve this is with a table that looks a bit like this. But as a stepping stone to that, let's first use our Venn diagram. The first thing we're told is that 64% of the students own a bicycle. On the diagram, the bike owning zone actually consists of two zones, which we can label X and Y. And to say that 64% own a bicycle, we can write X plus Y equals 64. The next thing we're told is that 33% of the students do not own a car. Now, the non-car owning students are the ones outside of this car circle. They can be in zone X or in this outer zone that we can call Z. So what this statement is telling us is that X plus Z equals 33. We're also told that 21% of the students own a car but not a bicycle. This is referring to the students inside the car circle but outside of the bike circle. So let's put a 21 in this zone. And finally, the question is asking what percent of the students own a bicycle but not a car? This is referring to the students in zone X who are inside the bike circle but outside the car circle. So we can note down our question as X equals question mark. It looks like it's going to be hard to find X because we have 3 variables and only 2 equations. Luckily, there is one more equation that we can squeeze out of the givens in this problem. You can see that when you remember that X, Y, Z, and 21 are all percentages of the total student body at College X. This means that X plus Y plus Z plus 21 equals 100% of the student body. And now that we have 3 equations, it is possible to solve for X. Of course, possible doesn't mean easy, and if, like most people, you'd rather not solve a system of 3 equations, you can turn to the alternative method involving what's called a contingency table. For this problem, one of the headings would be bike with subheadings yes, no, and total, and the other heading would be car with the same subheadings. In fact, you can use these same subheadings, yes, no, and total, anytime you make one of these 9-cell tables. Yes means you're in a set, no means you're not. Okay, so what do these 9 boxes mean? Well, this one, the no bike, no car box, corresponds to this area in our Venn diagram. These are the people who have neither a bike nor a car. In contrast, this yes, yes box is for the students who have both a bike and a car. As for this one, the yes bike, no car box, it's for the students here who do have a bike but don't have a car. In contrast, these students who have a car but not a bike belong here, where it says yes car, no bike. The rest of the cells are totals. Each of the cells in this bottom row is the sum of the 2 cells above it. And each of the cells in this right column is the sum of the 2 cells on its left. So for example, this cell, the total of the bike yes column, is the sum of green and blue, which is everyone in the bike circle. This one is the bike no total, so it's the sum of yellow and pink, which is everyone outside the bike circle. And here, the car yes total is green plus yellow, or everyone in the car circle. While here, the car no total is blue plus pink, or everyone outside the car circle. Finally, this cell is the grand total. You can get it by adding across. Bike owners plus non-bike owners is everyone, or you can get it by adding down. Car owners plus non-car owners is again everyone. Alright, let's ease into using these tables by tackling a simplified version of this problem. Let's say that 3 people own both a bike and a car, 5 own just a bike, 7 own just a car, and 4 own neither. This scenario isn't exactly a problem because I've told you all the numbers, but let's transfer these numbers to our table so we can better understand how the table works. Adding vertically, we have bike yes 8, bike no 11, and then adding horizontally, car yes 10, car no 9. Then this grand total can be thought of in 2 ways, 8 plus 11, 19, or 10 plus 9, also 19. Alright, now that we've warmed up, let's go ahead and solve the original problem. Notice that all the figures we're given are percentages of the students at college X. To keep all the numbers consistent, let's call this box the grand total of all the students, 100%. Okay, the next figure we're given is that 64% own a bicycle. This is talking about the total of the bike owners, so let's put it down here. We're also told that 33% do not own a car. This is about the no car total, so let's put the number here. And then we're told that 21% of the students own a car but not a bicycle. So these are the yes car, no bike students who are here in the yellow box. Finally, the question is asking what percent of the students own a bicycle but not a car. These students are yes bike, no car, so they belong in the blue box, and to indicate that this is the figure we're looking for, let's put in an oval. And now let's go ahead and solve this. The key is to remember that every row and every column adds up to its total. So if you have 2 out of 3 boxes, you can always find the third. Right now we have 2 out of 3 elements in the bottom row, so let's start here. This is saying that 64 plus blank equals 100. That means that blank has to be 100 minus 64, or 36. And now that we have 36 here, we can solve this column. The column is saying 21 plus pink is 36, and that implies that pink is 36 minus 21, or 15. Finally, this row is saying circle plus 15 is 33, so circle must be 33 minus 15, 18. And there you have it. The percentage of students who own a bicycle but not a car is 18. Notice how the table allowed us to find this with just a bit of arithmetic. This is quite a contrast to what we had to do before when we relied on the Venn diagram. There we had to have 3 equations in 3 variables. The reason the Venn diagram requires all this algebra is that it just has 4 spaces. The only number from the problem that could be placed directly in the diagram was this 21%. All of the other numbers, the 64, the 33, the 100, are combinations of these four colors, so they had to be represented by equations. With the table, we don't have this problem, thanks to all these extra cells. The 64, the 33, the 100, we can put these directly in the table and thus avoid a bunch of algebra. So the main takeaway here is that when you have two overlapping sets, you should make a table rather than a Venn diagram. The situation is quite different when you have a problem with three overlapping sets. For those problems, you do have to make a Venn diagram. You shouldn't worry about those now though, because they make up only 5 to 10% of the overlapping sets problems on the GMAT. For now, you should just practice the two-set problems, and then later, when you're ready, you can come back to part 2 of this video where I'll explain the three-set problems. In the meantime, thanks for watching this video from Chiron Prep. I hope you'll like and subscribe, and if you have a question or a suggestion for a future video, go ahead and leave it in the comments. If you're interested in tutoring, there is a link in my bio. Alright, good luck and see you next time.